Hi, I'm Ms. Vung. Let's have a look at the factor theorem. Have a look at these two sets of values. Here we have 12 divided by 3 and 12 divided by 5. What can you see? Is it 3 and the 5 factors of 12? Well, when we divide 12 by 3, we obtain 4 with a remainder of 0. And we know that 4 and 3 are factors of 12. So when the dividend is divided by divisor and you get a quotient with no remainder, then the quotient and the divisor are factors of the dividend. I'm going to say one more time. So when the dividend is divided by divisor that gives no remainder, then the quotient and the divisor are both factors of the dividend. Let's try a non-example. So 12 divided by 5 is going to give us 2, remainder 2 over 5. And we know 2 and 5 are not factors of 12. So when you divide by number and you get a remainder, then these numbers are not factors of 12. So recap, remainder means not factors. 0 remainder means factors. Keep this in mind as we go through this video. So here is an example from the previous video where we had that divided by that, and we use the remainder theorem to find the value of the remainder. This is from the previous video. So to do so, we let the divisor equal to 0 and we plugged in that number, minus 5, and we obtained a value, and in this case it's 0. So what can you say when it's 0? We could also see it from another perspective where we wrote a p of x equals x minus a times the quotient plus the remainder. We notice that if the remainder is 0, that disappears, then look, this times this gives us that. Or in other words, the divisor and the quotient are both factors of our dividend. Just like what we said about 12 divided by 3. When the remainder is 0, then our divisor and our quotients are factors of our dividend. So because this is 0, then x plus 5 is a factor of that polynomial over there. So let's write that down. Factor theorem. If p of a equals 0, then x minus a is a factor of p of x. Hope that makes sense now. If not, it's like saying when the remainder is 0, then 3 is equal to a factor of 12. Similar to that. Conversely, if x minus a is a factor of p of x, then p of a equals to 0. We can complicate this statement or make it a little bit more accurate by putting beta x minus alpha instead. So if beta x minus alpha is a factor of p of x, then p minus alpha over beta should be 0. So again, if p of minus alpha over beta is equal to 0, then beta x minus a is a factor of p. So same thing pretty much, but now we have a coefficient for x. Example 2, show that x plus 2 is a factor of that polynomial and hence find the other linear factors. So how do we do that? We use a remainder theorem. We hope to get 0. If we do, then we can say it is a factor. So p of minus 2 is, so plug in minus 2 wherever you see x, so minus 2 cubed plus 9 times minus 2 squared plus 26 times minus 2 plus 24. So we will obtain minus 2 times minus 2 is 4 times minus 2 is minus 8. Then minus 2 squared is 4 times 9 is 36. Minus 2 times 26 is minus 52 plus the 24, and sure enough we get 0. So if we set 0, we can state from the factor theorem that x plus 2 is a factor of p of x. We can then do long division to find the other factor or the quotient. So let's see if you remember this. So x into what is x cubed, that's x squared. So put in x squared there. Then we multiply. X squared times x is x cubed. X squared times 2 is 2x squared. Then we subtract. 9 minus 2 is 7x squared. I won't bother subtracting this because it just cancels out. Then again, x times what is 7x squared? That's 7x. So we plug in 7x over there. 7x times x plus 2 becomes 7x squared plus 14x. Then we subtract. 26 minus 14 is 12x. X times what is 12x? That's 12. multiply it through. 12 times x plus 2 is 12x plus 24, which gives us a remainder of 0. If you've just done the remainder theorem by plugging the number and getting 0, and you do long division and you don't get 0, you know you've made a mistake. So you can go back and check your answers. But if you do get 0 like we did so, you should feel pretty happy right now. So now that is the quotient. So that's a factor and that's a factor. So now we can write down our long polynomial is equal to that times that. And we can use quadratic factorizing. So what two numbers multiply to give 12 but add to 7? So 3 times 4 is 12. 3 plus 4 is 7. So we can further factorize and then obtain our 3 linear factors. So recap. Remainder theorem. Check for something that gives you 0 as your remainder. If you found it, then you also have found your factor. Now that you found the factor, plug into the long division to find your quotient, and then you can write your divisor and your quotient together, and then make sure you further factorize if you can. Let's do another example. Example 3. Factorize x cubed minus 21x plus 20. So here again, we're looking for that remainder to be 0. So let's try, we know previously, if I go back, that the factors of our polynomial, how do you get that last coefficient? You can get that last coefficient by multiplying through the terms that have no x's. So 2 times 3 times 4 is going to give us 24. So we also know that the factors, or our first factor that we look for, should be a factor of the last term. So in other words, when we look over here, it should be 1, 2, 4, 5, 10 or 20, because it should be fitting into 20. So we're only going to try those values. We don't try 3 because 3 will never give us 20. So let's try the first one, 1, and sure enough it gives us 0. So we know straight away that p of 1 giving us 0, that x minus 1 is a factor of p of x. And now that we have the divisor over there, how do we find a quotient? We use long division. You can use the synthetic method or any method you want, it's fine. And we have to be careful because there's x cubed and then 0x squared. Remember to put that in. Then minus 21x plus 20. So let's put in our divisor and let's go x times what is x cubed? That's x squared. So x squared, multiply all that, we get x cubed minus x squared. Subtract. Minus minus becomes a plus, be very careful. So now we have x squared. X times what is x squared? That's just x. So plug in x over there. So x times x minus 1 becomes x squared minus x. Now we subtract. Minus 21 minus x, which means minus 21 plus x will give us plus 20. Sorry, minus 20x. And then x times what is minus 20x? That's minus 20. So minus 20 times that gives us minus 20x plus 20, subtracting, and it gives us 0. So now we can write our dividend is equal to our divisor times our quotient, and we think what two numbers multiply to give us minus 20 and add to give us 1? That's minus 4 and 5. Now try the next example yourself, pause the video and unpause when you're ready to see the answers. So first of all, look for the first divisor, which has to be a factor of 20. So 1, 2, 4, 5 and 20, there's no point trying 3. So we try 1 first and see if it fits. So 1 cubed plus 5 times 1 squared minus 4 minus 20, and we notice it doesn't give us 0. So x minus 1 is not a factor of p of x. Remember at the start where we did 12 divided by 5 and it didn't give us a 0 remainder, so it wasn't a factor? Same kind of pattern here. It's not giving us 0, so that's not a factor. So we have to try something else. So let's try 2. If we plug in 2, we obtain 0. So then x minus 2 is a factor of p of x. So you'll notice that not always you'll be lucky and get the factor straight away. So just keep trying all the factors of the last value. Now what do we do after we find the first factor? We do long division of x minus 2 and all of that. So x times what is x cubed? That's x squared. X squared times that is x cubed minus 2x squared. Subtract. 5 minus minus 2 is 7. Then x times what is 7x squared? That's 7x. And then 7x times that gives us 7x squared minus 14x. Then subtract. Minus 4 minus minus 14 is plus 14, gives us 10, which is what we wanted, because x times what is 10x, that's 10. And when we multiply through, we get 0. So now that is our quotient. So that is a factor, and that x minus 2 is a factor of our polynomial. So we'll write that out is equal to x minus 2 times our new pretty quotient. And then we factorize it by saying what two numbers multiply by 10? That's 2 and 5, and add to 7. Okay, this one is a little bit tricky, so be very careful. Again, we try factors of 3, and we notice that doesn't matter what number we try, you can use a calculator to try it, that we never get 0. And then we look at this and we notice there's a number in front of 2. So remember how when we were looking for the remainder theorem, that we would plug in, we would let 2, for example, if we had x plus 3, then we'll let x equals to minus 3. But if we had 2x plus 3, what did you plug in? Minus 3 over 2. So likewise, rational root theorem. So rational, what does that mean? You can put it as a fraction. That when beta x minus a is a factor of p of x, then we notice that the beta divides a, or is a factor of a, so the first value, and alpha is a factor of the last value. So now we're going to look for things that the top number divides the 3, the last number. So I said the top number is still correct, but now we have to have a denominator which divides 2. So instead of these numbers, let's try out 3 over 2. And surely if you put 3 over 2 into where x is, so 2 times 3 over 2 cubed, etc., we are going to get 0. So 2x cubed minus x squared minus x minus 3 is going to be x minus 3 over 2 as our first factor. And when you do long division, you'll obtain this part over here. I'll skip that pattern. You can practice from example 1 to 4. I just want to go through what happens in this scenario. So recap. If you have a number in front of the first term, so top number divides the last bit, bottom number divides the first bit, and then do long division. And sometime you'll get something like this. And how do you show that you cannot factorize it any further? You will have to say that the discriminant is less than 0. And you have to show that. You have to write down b squared minus 4ac is 1 squared minus 4 times 1. So it's minus 3. And minus 3 is less than 0. So you actually have to write minus 3 is less than 0. And the discriminant is less than 0. So no more further factorizing. Thank you for watching. And you might want to try this question again. And when you're trying, use a calculator for this part and actually expand and show to yourself that it gives you 0. Write it out like that and write down the working out for the discriminants, and so that you have the statement the discriminant is less than 0 and you cannot further factorize. So try this again, and I'll see you next time. Bye!